In this video, this is going to be part of lesson 2-6. We're going to look at similar triangles, and we're going to look at similar triangles in the coordinate plane. So the first thing we're going to do is we're going to look at similar triangles. And what are similar triangles? Similar triangles, remember the word similar. This means that they are the same shape, but they're not necessarily the same size. So when we have objects that are similar for our purposes, we're talking about two objects that are the same shape, but they're not the same size. For example, every square that you draw will be similar. Every square in existence. Why is that? Well, every square is going to be the same shape because the square has, first of all, the same four angles, but every square that I draw is going to be of the same shape, the same type of, not dimensions, but the same type of ratios because all the sides are the same. And I could keep going and going and going. I could draw another square. So that's what similarity looks like in squares. Well, we obviously have the possibility of similarity in all figures. So we're going to focus on triangles. And in particular, in the coordinate plane, we're going to focus on right triangles. So these are what we call in the coordinate plane are going to be called dilations, but we'll get to that later. So let's just talk about similarity first of all. Same shape. So I'm going to give you a triangle, and I'm going to call this triangle ABC. And I'm going to give you another triangle, and make this one a little bit bigger. And I'm going to call this DEF. Now these two triangles are similar if, first of all, in triangles, and this works in triangles, it doesn't work in every type of shape, if all three angles are the same. So if we can establish, first of all, this is one possibility, and remember this is how you mark angles are congruent, you use arcs. If I can establish that these two triangles have the same three angles, then I can establish that they're the same shape. So, with that being said, let's look at sides. So looking at sides, well, I'm going to give you some ideas here. Let's say that this side is 2 and this side is 4. And let's say this side is 4 and this side is 8. And let's say that this side is 5 and this side is 10. So the question is, do I know if these two triangles are similar or not? Let's say I don't know the angles. Similar figures have what we call a common ratio. Okay, I'm going to write that for you. They have a common ratio. Now what that means is if I were to proportionally set up all of these sides, they would all be equal. Basically, whatever I did to each one of these sides to get each one of these sides was the same thing. And that's going to give us what we call a scale factor. And I'm going to show you what this is. So a scale factor is calculated by taking the image. And if you guys remember when we talked about transformations, the image is the new object. And we're going to divide that by the pre-image, which is the old object. So for me to get my scale factor, I'm going to take new divided by old. So let's start off with 8. New is 8 divided by old, which was 4. And right now I'm going to match these up by location. But keep in mind that the triangles are not always going to be oriented the same way. This triangle right here might be flipped upside down and E might be down here. You have to pay close attention, but I'm making it simple since we're just starting out. And 10 would have to go with 5. And 4 would have to go with 2. So, if all of these ratios right here, all three of these ratios, if all of these guys are equal, that means that there exists a common ratio which is called a scale factor at times, depending on how you write the common ratio. Ratio is kind of a word that can be confusing at times because a ratio is basically a comparison between two numbers, like any fraction that you have is a ratio. But ratios can also be written like this. And it depends on what you're designating for those values, whether the ratio written like this is the same as the fraction written like this. But we won't get into that in this lesson. So let's look at these. 8 over 4, if I reduce that, that's 2. 10 over 5, if I reduce that, that's 2. 4 over 2, if I reduce that, that's 2, which means all three of these ratios are exactly the same. Therefore, these two figures, these two triangles, are in fact the same shape. They are similar, okay? They are similar. Now, because we've established they're similar, I can also say that 2 is my scale factor, and we actually use the letter K to indicate the scale factor. So 2 is my scale factor because I basically multiplied the first triangle by 2 to get the second one. So that's how the scale factor works. So let's come down here and let's do another example. I'm going to draw 2 more triangles for you, and I'm going to keep this simple at the beginning, and then we'll get a little bit more complicated. So let's do this with this triangle here. And I'll call this triangle PQR, just so we can get used to naming them. And then I'm going to have a second triangle. And look what I'm going to do. I'm going to flip it around. JKL, because I'm so original with my names. And I'm going to give you a statement over here. I'm going to tell you that triangle PQR, and here we go, this is the symbol, is similar to triangle JKL. Now, if you look at the similarity symbol, do you remember when we did congruent? Congruent looks like this, right? Well, congruent is not just same shape, it's same size and same shape. Hence, when you look at this, it's got the equals component, which indicates the same size, and it's got the similar component, which indicates the same shape. So when we're talking about similarity, we're only talking about the shape. So that's just some food for thought there with the symbols. So if I tell you that PQR is similar to JKL, that's how I'm going to match up my sides, just like we did with congruent triangles. So that means that PQ matches up with JK. And it means that QR matches up with KL. You can see how I'm matching them up. And it means that PR matches up with JL. So when I find that common ratio or that scale factor, that's what I'm going to be comparing. So I'm going to go ahead and give you some sides here. Let's make this a 3, 4, 5, excuse me, 3, 4, 5 triangle, as I'm coughing up my lungs here. And we'll make this a 9, 15, 12 triangle. So I've already told you they're similar, which means that there's going to be a common scale factor. I'm going to write this again so that you see it again. A scale factor is when we take the image, which is the new, and we divide it by the pre-image, which is the old. It's very important that you put the new image on top. And again, we indicate this by the letter K. So by our purposes, looking at the picture, the purple one is the new, is your image, and the blue one is the pre-image. So when you look at these ratios of these sides, what this means is, because I've matched these up, I'm going to write an equality statement based on these. So we've established that PQ goes with JK, right? So that means that when we do our ratios, PQ and JK have to be together. Now, if I'm trying to find a scale factor and I want to know how I went from the old to the new, remember, the new one goes on top. So between PQ and JK, which one is the new one? JK. So I'm going to have JK over PQ. And then that should be equal to these two. And remember, KL is in the new one, so KL over QR. And technically, if I want to be correct, we won't use these symbols because remember we're talking about, so I'll write it correctly, because we're talking about the lengths, not the objects. We're actually talking about their lengths. And so that equates to JL over PR. So all three of those should be equal if these are similar figures, and it'll tell me what my scale factor is. Well, I've already told you up here that they are similar. But let's just plug everything in and see what we get. So let's start off with JK and PQ. JK is 9, and PQ is 3. Now you see how these triangles are not oriented the same way, so you have to read the similarity statement. KL, which is 12, goes with QR, which is 4. And PR and JL go together, so 15, which is JL, goes with PR, which is 5. So, are these all equal? Well, how do I reduce them? 15 divided by 5 is 3. 12 divided by 4 is also 3. And 9 divided by 3 is also 3, which means check, check, check. They are similar. And your scale factor is 3. Whoopsie. Your scale factor is 3. Now what that means is I took the original figure and multiplied it by a factor of 3 to get the new one. Now that is called an enlargement. And you guys have talked about photos before. An enlargement is when something gets bigger. You make it bigger. And a note for the enlargement. Enlargements happen when your scale factor is larger than 1. Why does this make sense? Well, if I'm multiplying by 1, then my figure doesn't change, right? If I multiply everything by 1, it's the same figure. If I multiply by something larger than 1, my figure is going to get bigger. It's enlarging. But what if I did something less than 1? So let's check that out. I'm going to give you another set of triangles. So let's start off with this triangle. And I'll give you another right triangle since we're going to be kind of dealing with those. And I'm trying to think of some numbers that I could give you. Let's see here. Okay, so let's say that this is 32, and this is 60, and this is 68. And let's say I give you another triangle, but this guy's smaller. And I'll line these up. And I have 8 and 15 and 17. So now I'm going to tell you, I'm going to go ahead and give you the similarity statement. And let's make this COW. And let's see, MAT. Why not? Makes no sense. So triangle COW is similar to triangle MTA, and I'm telling you that. So knowing that, let's set up our little ratios. So which sides go together, first of all? Well, I know that CO has to match up with MT. Now remember, this is your image. The second one is your image where you finish up. So the MT will go on top. So I know that MT over CO has to be equal to, I have OW and TA. Well, TA's here. TA, oops, my bad. TA, let's try this again. TA over OW. And that has to equal AM over WC, or MA over CW, however you want to do it, doesn't matter. MA over CW. So since these triangles are similar, all of these should be the same. So they should all be, I should be able to plug into all of these and find my scale factor. So let's look at MT over CO. MT is 8, CO is 32. So 8 over 32 should be the same as TA, which is 15, over OW, which is 60. And that should be the same as MA, which is 17, over CW, which is 68. So you can see now that these are going to be less than 1. And you know that the figure got smaller. Well, let's reduce these and see what we get. 8 over 32 actually reduces to 1/4. 15 over 60 actually reduces to 1/4. And 17 over 68 reduces to 1/4, which means that our scale factor is 1/4. Now, what do you notice about the scale factor? It's less than 1, right? That's because this is called a reduction. A reduction is when the scale factor is less than 1. If I multiply by 1/2, 1/3, 2/3, 5/7, anything less than 1, like I did in this case, 1/4, the figure is going to get smaller. So this is how you find a scale factor and set up proportionality using similar triangles. One thing that we will do for College Board is we will actually have similar triangles in the coordinate plane, and I will create the next video for that. But this is how we do similarity for triangles.